So here we are. So we have been so we spent the last lecture talking about energy scales and why the nanoscale regime is particularly interesting from the point of view of the convergence of different types of forces and energies. And what this means in biological context, but also generally in the field of nanotechnology, is that confinement, nano confinement, at the nano length scale, thermal fluctuations can easily facilitate the conversion of one form of energy into another. And this is what nature takes full advantage of. We then looked at something known as the Bjerrum length, the length scale within a continuum classical dielectric picture where electrostatic energy gets much larger than thermal energy. What we learned from that, what we sort of inferred from that is that this is actually one of the core reasons why in the field of structural biology, biochemistry, people spend a lot of time trying to understand specific molecular interactions, because it's these specific molecular interactions at these scales, at these length scales, where they can get significantly larger than thermal energy, so they can drive processes in very specific directions. Now, having said that, one of the big assumptions, of course, that we're making in this whole discussion is that I can treat the environment as a continuum dielectric. Why should that be the case? Is there a length scale at which the continuum dielectric picture breaks down? One might think that when you get to the length scale of less than 1 nanometer, that might be the case. And the answer is yes, and it depends on what type of problem one is looking at and what type of interactions one is looking at. But as a zero order first way of understanding the relevant energetics and length scales, this way of looking at the problem allows you to get a feel of those numbers. And so later on, probably actually next week, we will spend some time looking at this more from the perspective of modeling. So we will examine, going from continuum dielectric models to atomistic models to models where you include electronic degrees of freedom, and just try to understand a bit about, the various challenges that you get when you go from more accurate but to more computationally expensive. Okay, I just want to say one last thing before we switch gears a bit on what we're going to be discussing today. There's something, if you have one of the things we discussed is in the cell, of course, that there are a lot of ions. There's a high concentration of ions. And one of the interesting or sort of problems in biophysics is understanding how ions screen charge. And this goes back to the problem I showed you in the first class, where I have a virus capsid. And in that capsid, which is about on the order of tens of nanometers, I have to pack and coil a micrometer of negatively charged DNA into this small region. How does it do that? How do you think about the ions and how they screen the charges. What is the charge density profile? What is the potential that the ions create? So this is something that we're going to come back to next week, but because of the similarity in the length scales, I just wanted to point this out. There's some of you might be familiar with this. It's something known as Poisson-Boltzmann theory. So Poisson-Boltzmann theory is a continuum theory that combines Poisson's equation from classical electrostatics and the Boltzmann equation from statistical mechanics, and asks the question, if I have a charged object like a DNA or an electrode or a protein, and if I have counter ions around them, what is the distribution of the ions around that charged particle? And so you can use this continuum dielectric sort of mean field theory and show that that there's this length scale known as the Debye Screening Length. And the factors that control this Debye Screening Length are, well, no surprise, the dielectric constant, thermal energy, and then there are these factors here that in the bottom that correspond to the electronic charge and the number of valence charges. So, for example, in sodium, this would be +1. In chloride, this would be -1. So this is an integer. And C infinity is the concentration of the ions in the bulk. So if we took those numbers of the concentration of ions in the cell, we discussed some time back, which is about 100 to 200 millimolar, and we plug in thermal energy, we plug in a static dielectric constant of 80, you get that the Debye screening length is about 0.7 nanometers, so 7 angstroms. So it's very similar to the Bjerrum length. Okay, and essentially the physics behind these the screening length associated with ions is, of course, must be and should be very similar to the screening of two charges in solution. Okay, so we're going to come back to this, but I just wanted to point out this length to you because it's the length scale of 1 nanometer or so is a recurring theme in our discussion. Okay. So I think I also mentioned this, but I'll just repeat it for completeness. Van-der-Waals forces, so non-electrostatic interactions, so where quantum mechanical fluctuations and correlations in electron density are a big part of the intramolecular forces that affect biological systems. And even though they're individually weak, for example, the Van-der-Waals force between two methane molecules is the binding energy is less than a kilojoule per mole. It's less than kBt. It's very weak, but there are many of them in biological forces, and many of them can contribute and add up. So this is on one side. On the other side, when you start to put non-polar molecules like methane in biological systems, so imagine that you had a methane hydrocarbon, so an oily molecule, and it was near some charges. Then, because of very subtle and important electronic effects, the non-polarity of what you think of as non-polar changes. And so in the chemistry community and also in the biology community, you know, the role of electronic fluctuations in modulating the interactions of things that are referred to as nonpolar, something that's really not well understood. But they play a very, very important role in stabilizing biological assemblies. Okay. And yeah, just to, if you're looking for a nice, well, Friday evening or weekend read, this is I highly recommend this article. It's just been published last year, a year and a half ago, and it's a paper that examines the role of many body Van-der-Waals forces in biological systems. So remember that most of us, in fact, all of us who've studied Van-der-Waals interactions in the context of most of our numerical work, usually we start from the Lennard-Jones potential, right? This is a pairwise interaction where the only attractive part of the Van-der-Waals is this -1/r⁶ term. And this is strictly a pairwise interaction. It turns out that, and what this paper tries to show is that there are some very interesting, subtle, long-range, many-body Van-der-Waals interactions that play a very important role in protein folding, for example. And the reason I like to highlight this, because this is it really shows you, it's a nice example of how really fundamental physics from the point of view of electronic structure. So I say this for the diploma students because they're taking a course now in electronic structure, how that interfaces with interesting questions and problems in biology, okay? Where the challenge is less to do with the biology and more to do with understanding, you know, how to treat Van-der-Waals forces correctly in a collective sense. Okay, good. So this is that. So so we're going to switch. Are there any questions before I move on to something else? Okay, no questions. Good. So let's review. The cell is crowded. I've convinced you now that there's hopefully that lots of water, lots of proteins, lots of ions. All these interactions play a very important role. And this means and has implications on the typical distances that separate these species in solution. So now we're going to backtrack a bit, and we're going to go back to understanding a bit about the environment, i.e. water. Not from the perspective of really from a biological context, but more from some basics that that we all have learned about in the past, but we're just going to refresh some of those things so that we gain an appreciation of the complexity of the thermodynamics and dynamics of the environment, that which is what makes up the cell. Okay, so why is it that people have been obsessed with understanding the properties of water for centuries, essentially? And every year there's a new puzzle in in the field of both experimental and the theory side of water. And so let's walk through some properties and some features that make it an interesting object to give a second look at. So we talked about dielectric constants. Dielectric constants are related to the ability of the liquid to be polarized by electric fields. And I'm just showing you here many different liquids. Half of them I've never heard of, but they exist. And what you see is that water has a large dielectric constant. Okay, compared to most other liquids, water is very polarizable, and this is an extremely important feature of it. You know, forget near a protein, forget near a molecule. Its intrinsic polarizability, both orientational and electronic polarizability, is at the heart of why it is able to do chemistry. There's a reason why chemistry works in mostly in water, and the reason is rooted in its very high ability to be polarized. Okay, and then this has implications on other things that you're going to see shortly. So okay, that's dielectric constant. What about heat capacity? Okay, so sorry for the bad picture, but water has a very large heat capacity. So apart from ammonia, water's heat capacity is much larger than other liquids, and this large heat capacity is at the heart of the fact that it has many different modes in which energy can be dissipated into, which is what makes it a very good bath, a thermal bath. And so when you have a biomolecule living and breathing in a liquid like water, it's not as susceptible to large temperature fluctuations. So if you dump some energy into a particular mode in a protein or a molecule, that energy can very efficiently and quickly dissipate into lots of different vibrational modes in liquid water. And this would not be the same or the case for example, life in, what do I have? Formamide here? No, I don't have formamide. But if you were to imagine how a solvent with a low heat capacity would be able to dissipate heat, there would be, many challenges in doing that, and this would have many other implications. Okay, so its heat capacity is large. Water has a high heat of liquid vaporization. So essentially, and so this is given by, these are the curves showing the molar enthalpy versus temperature of different liquids. And so the energy required to take 1 gram or a certain amount of water and convert it into the vapor phase is much larger compared to other liquids. And this is a great thing because it's the reason why when you sweat mostly water and it evaporates, it takes up a lot of heat from your skin. So if you were sweating benzene, this would probably not be a good thing, and you would not be able to cool down as effectively. Okay, so that's number 3 in terms of water having some very different and interesting properties compared to. Now, let me add, okay, benzene. Okay, benzene is a non-polar or inorganic, non-polar solvent. Methanol is also has hydrogen bonds. So we're going to come back to, water, of course, is held together by these dipole hydrogen bonding networks interactions. So is methanol, but it's not enough just to have, hydrogen bonds. There's more that's needed to give water its anomalous properties, which we will shortly discuss. Okay, so high liquid vapor vaporization. Okay, this is something
So what is the characteristic that makes water has high liquid vapor?
I sort of alluded to it, but basically it has a very dense network and collection of hydrogen bonding structures. And hydrogen bonds they form a collective network, and breaking up a collective hydrogen bond network costs energy, which is missing in the other liquids. They're held together by much weaker forces.
But I suspect that acetone has higher hydrogen bonding than benzene. That's why benzene has
Let's go
higher.
back. Hydrogen, acetone. Wait, I need to remind myself what the structure of acetone is. Okay. Acetone, hold on. Acetone. So acetone looks like this, just for the sake of everyone.
I think it has one ether functional group.
It has 2 CH3 and 1 CO.
Yeah.
So no, it can't. So methanol, so acetone cannot form a hydrogen bonding network as easily.
So it can polarize at the oxygen.
Yeah.
Oxygen, right? And then it also has a hydrogen atom
in
other molecule.
No, in acetone, the hydrogens are on the methyl groups.
Yeah, but I mean, like, okay, so now the more polarized will be on CO.
Yes.
And then okay, so it's more negative. And
but okay, but if you bring lots of acetones together, right, in a liquid, the only way that acetones can interact with each other is that the CH bonds of the methyl will have to donate weak hydrogen bonds to the CO group, to the oxygen. So CH bonds are very so carbon is not as electronegative, right, as oxygen.
Okay, so now oxygen will attract electrons from the the middle carbon, and then the middle carbon will lack of electrons, and then it will attract some electron from 2 other carbon, and then it will it will deficit the electrons
Right.
in the two other carbon, and
Yes.
then two other carbon will attract more electrons in hydrogen, and hydrogen now will become a bit. I expect that it will become a
It,
bit
it,
positive, and
yeah.
the oxygen will be now more negative, and then they
Yeah,
will
absolutely. So what you say is correct, but the CH dipole that you just created because of this electron restructuring is much smaller than the OH dipole that you'd have in methane. Sorry, methanol.
Yeah, I agree, but I want to compare with the benzene. Benzene,
Oh,
I
wait.
expect that it has no
Hold on,
hydrogen
wait.
bonding.
Let me see benzene. Benzene at room temperature. So benzene has a so probably it has to do with that the Van-der-Waals. So in benzene you have pi stacking.
Yeah, I agree.
So it's a subtle balance between this
Six carbon.
between the let's say the polarization that may lead to weak electrostatic interactions in acetone, and at the same time probably some collective Van-der-Waals pi stacking that is clearly stronger.
Oh.
So I don't have a precise answer for you, but that maybe my inkling is that it's because of pi stacking that leads to some stronger interaction.
Okay, I will. I think I will think
Yeah,
more about this.
yeah. It's a good question.
Thank you.
Thanks. No, thank you. Okay, very good. Okay. So our intuition tells us that as you take a liquid and you increase the temperature, the density should decrease, right? And that's what happens in ammonia, methanol, dimethyl ether. This is just another liquid. Don't worry about the chemistry here. So most liquids, as you increase temperature, the density decreases. Okay, but and probably this is one of the anomalies that you're all most familiar with, which is that water has a normal behavior after some temperature in terms of the density, but it has this weird peak in the density at 4 degrees Celsius. Okay, so all this region below 4 degrees Celsius is anomalous. It's counterintuitive. Same thing for the compressibility. So the isothermal compressibility increases for normal liquids as you go higher in temperature, but water has this weird thing, which says that when you go to below some temperature, the compressibility increases again. Same thing for the heat capacity. So, so these are the most commonly talked about and discussed thermodynamic anomalies in water. And while you might say at cellular or thermal conditions, do any of these anomalies really play an important role? Well, this is an open question, and part of the challenge is people still don't really understand what is the exact thermodynamic landscape and dynamic landscape of water in crowded environments, like in the cell. Okay, so we don't know what that is, because it's a very challenging experiment. It's not been done yet, but also very challenging from the point of view of simulations. So what's the origin of these anomalies? Well, again, the exact microscopic anomalies or origins of these anomalies are still hotly debated on. One of the common discussions and ideas that has come from the more physics community is that you can understand these anomalies in terms of two coexisting phases of water. And so in the high temperature limit, there's one particular phase that dominates, and then as you go to the lower temperature, there's a transformation into another phase. Okay, but this is a very controversial area and still not completely understood. Okay, so those are the more physics language and physics community-based discussions on the anomalies of water. But there's another side of this, which is the chemistry side. Okay, and this is something that sometimes the physicists well, don't quite appreciate so much, and that is the role of pH. So water, every 10 hours dissociates. It dissociates to form a proton and a hydroxide ion by this equilibrium. And this dynamic equilibrium is what determines pH. Okay, and pH has a huge role in biological problems, and one of its main roles is in altering the chemistry of the elements, some of the elements of proteins and peptides, and even DNA. So, so if you go back to, well, I assume I haven't actually officially taught this in this class, but this is basically a peptide. Peptide proteins are made up of many of these peptide groups, and the peptide groups have this amide bond, which has there's an NH and a CO. Okay, and these NH groups and these CO groups, let's say, in a very hand-waving way, for now, have the ability to exchange or have an equilibrium with protons in the bath. So if you want to think of this in terms of a bimodal two-state problem, it's exactly the same thing here in this case, but now you have a situation where protons can be either stuck on the peptide or they can be in the bath. And depending on pH, you can change this thermodynamic stability of which is the main protonation state of the peptide. And this is tied then into electrostatics, because the moment you start adding and pulling off protons from a peptide, you change the charge. Something can become positively charged, something can be neutral, something can be negatively charged. And this then has effects on all the screening lengths and all the sort of the length scales that we were discussing before. So acid-base equilibrium is a very important aspect of how water is very unique. Not all liquids are able to do this. Okay, this is a very peculiar property of water. Okay. And so I basically, well, sort of alluded to this, but there's the stabilizing forces then for biomolecules in aqueous environments involves a very subtle balance between these enthalpic interactions. So, you know, electrostatics, Van-der-Waals, charge transfer on one side, and entropic factors. So in how many different ways you can reorient and organize water molecules around something that is oily versus something that is not oily. Okay, and this balance of these two things ultimately determines the free energy, right? And that free energy is what determines then in which direction your biological system is going to move. So I hope, you know, so you're beginning to see that, you know, that in many of these biological systems in environments like water, there's this underlying there are many of these underlying contributions to the enthalpy and the entropy that ultimately affect the free energy. So just to make it a bit more concrete, so if you take I've mentioned to you the protein folding problem, right? So a protein polymer is unfolded and then it collapses into, you know, something that's a folded structure. That if a protein has a stable three-dimensional structure, then its folded state is lower in free energy than its unfolded state. The typical free energies between folded and unfolded states are not so large. They're like on the order of 10 kBT. That's not large. Okay, so it's a small number. It's a small number in terms of free energy to stabilize a folded versus unfolded state, 10 kBT. But if you disentangle the change in enthalpy and the change in entropy, those come from very large numbers on the order of hundreds of kBT. So entropy and enthalpy balance each other out because they're coming from many different contributions, and those many different contributions, a big part of it is the things involving the solvent. And so often that's it's a bit masked away or swept under the rug, but but it's a balance of these two competing factors that ultimately control the eventual thermodynamics of the system. So one last point here, just like
yeah, could you please tell more which process will affect the entropy and which process will affect enthalpy?
Okay, great. Great question. Okay. Yes. So I tried to give you a short answer now, and then it's something that we are going to cover later on. So let's look at this picture here. If you had, so here there's a dipole interaction between the water and the carbonyl CO group. Okay. If depending on the orientation of this dipole relative to the CO group, if I change the orientation of it, of course the enthalpy, the interaction energy would change. Okay, so that's one very simple example. Another example is which is related to the discussion that you and I were having earlier on. Imagine that you had a, let's go where, let me try to find something here, a hydrocarbon. Let's go back. Oh, here we are. Wait. Yes, here. So imagine that you had CH, methane in water. The CH is only weakly polarized, right? It doesn't have a large dipole, the CH bond. Yeah. So it will form weak enthalpic interactions with the dipole of the water.
Yeah.
Okay, but now here's where entropy plays a role. So so let's say the classical textbook picture is that the methane is inert. People don't imagine electrons on it. So basically water cannot interact with it. And because it cannot interact with it, there's a change in the number of orientations that a water can take if I have this oily molecule here, right? Versus when the oily molecule is not there. I don't know if you can see my hand tumbling. But so oil, let's see if I can, so this is the oil and this is the water. Because of the presence of the oil and it can't form interactions with it. My two fingers are the water molecule, the protons. It can't, it's restricted in terms of its orientations. But when I get rid of it, the number of orientations and that the or states that the water can take are increased. So what an oily molecule does is it reduces the orientational entropy of a water. And that's where entropy comes in.
So you mean that water will be in more order when it will be in methane?
That's correct. Exactly. This is the, let's say, the classical textbook picture, which, yeah, it gets about 70% of the story right, but that's the idea. Is that clear?
But I see here there is a exchange protons and I mean exchange acceptor and donor protons and something.
You mean in my slides?
Yeah.
This one. Yes.
And I'm suspecting that it will affect the entropy and enthalpy.
Absolutely. So this is yes. So now, so what protons exchange with so protons from the solvent can exchange with the water protons on time scales of what is it? I think it's minutes. So it's very slow. Unless you have a catalyst. So if you introduced a catalyst like a hydroxide ion, like this object here, then you can catalyze the exchange, but it's a very slow process. So if you're making measurements of your enthalpy and entropy of a process that's much slower than the time scale of proton exchange, then of course it's irrelevant. So it depends on the time scale of the process that you're interested in looking at the enthalpy entropy contributions. Is that Lian?
Actually, I still feel confused. Okay, so
go ahead,
I will express my thinking.
Yeah, please.
Okay, so I think entropy will entropy, like you said, it will be expressed by the order of the water. But for the case of methane, because it's a like in any order, it doesn't matter. So
Yes.
I think that water can be in any order. So I think a bit opposite to what you say, that water will be
no,
more
okay.
chaotic.
So okay, so you caught my lie, and so yeah, methane is a bad example because methane is small, but you're absolutely right that there's actually, this is known as the length scale crossover for where the disorder to order transition happens. So you have to have a sufficiently large methane or oily looking like object before my argument kicks in.
And for the case of this peptide, I think like this. Okay, so now we have the polarized because we have the CO and H functional group. So it will be a kind of polarized, and it will attract water. But when it attract water, it mean that it try to repulse. Like they become closer. So so the geometrical exclusion will want to repulse them far from each other. Like there's only one space, but they want to be close. So
okay.
Yeah, and that is the for the enthalpy part, and for the entropy, because they are in, the peptide bond is polarized. So if it will prefer one orientation, one specific orientation of water, so it will make water become more order, and it will reduce the entropy, and so the fact of enthalpy and entropy will be in balance in that case.
Well, okay, that's very interesting. So thanks for sharing those ideas. So let me try and digest it a bit. So I start with the second one, and so okay, there certainly there will be an entropic contribution that is different from polar groups of, so dipoles of the protein ordering the water around them. This I accept. But at the same time, there's an enormous entropic contribution that comes from things that are completely nonpolar. So because you can take a polymer that's purely hydrophobic, so without any polar groups, and it will still fold. It will still have a three-dimensional native structure. And why does that happen? That happens because of the entropic argument that I was making and that you caught, which is that once you get to some critical length scale of the non-polar surface, that results in an ordering of the water molecules around it. So there are two things going on there. On the enthalpic side, I'm less. I understand your argument a bit less because remember, these are not static objects, so they're fluctuating. They're undergoing lots of transitions, and so they're breathing. And so at some points there'll be favorable enthalpic contributions coming from one type of force. Other times it'll be something else. So yeah, I think yeah, I understand your argument of the enthalpy part a bit less, but maybe we need to discuss it more.
Yeah.
Okay.
Thank you.
Okay, thanks a lot, Lian. Okay, great. Okay, so now let's go back to something more physicsy, and something that is also not appreciated so much, and even worse, very poorly understood. And this is isotope effects. There are three types of water. There's light water, heavy water, and very, very heavy water. So H2O, D2O, and T2O. These are different. Deuterium and tritium are isotopes of water. It turns out that if you even have a very small, life does not survive in D2O. Proteins don't fold in D2O. Yeah, basically cells die in D2O, and which is rather interesting. And now if you look at, so the figure that I'm showing you is one of the anomalies, the density maximum of water. And you see that the density maximum of water shifts to higher temperatures. So it shifts from 4 degrees to 11 degrees Celsius. It's a huge shift in the density maximum of water. And so there are two questions. Why should you care about this in the context of molecular biophysics? And what's the source of this phenomena? So I tried to dig out this. Well, this is again an area that is still not completely well understood, but there were these old experiments in looking at. They do something called circular dichroism. Circular dichroism is an experimental technique that allows you to look at the secondary structure, the three-dimensional structure, well, three-dimensional, no, secondary structure of your protein. And so proteins are built up by different types of secondary structure, like helices, like in DNA, sheets, coils, and these are like, they're Lego pieces, basically. Lego pieces with different shapes. And take a look at this, the things that I've tried to highlight here. When you go from H2O to D2O, there's a big change in the percentage of helical structure in the protein. And the question is why? Why does a configurational property, so the helix, the sheet, is related to the distribution of the positions of the carbon atoms, the oxygen atoms, the nitrogen atoms, the hydrogen. Why does that change when I go from H2O to D2O? Is that surprising, first of all? And yes, it is surprising because in classical statistical mechanics, we know that the configurational part of the partition function goes as e to the minus beta v potential, which is independent of the mass. The mass does not enter into the configurational part of the partition function. So why does, what would cause a change in the sex structure? Well, obviously, this is saying that the classical picture breaks down, right? Okay. Another example. These are, I think, from the same paper, where they look at the free energy.
Sorry, I have a question.
Yeah, sure. Go ahead, Paul.
Yeah, what about when the potential has a mass dependence, like maybe for a harmonic oscillator, classical harmonic oscillator?
What about when the potential has a mass dependence? So how does in a classical harmonic oscillator, how does the potential depend on the mass?
Yeah, so the potential.
Classical versus quantum, let's compare.
Yeah, in the quantum harmonic oscillator, so there is no dependence on mass.
Okay.
Because it only depends on the omega and the frequency, and then
wait.
level.
But the frequency is related to, I thought it depends on square root of k over m.
In fact, yes, in fact,
so,
it also depends on, it has a mass dependence in the frequency.
In the quantum case.
Yeah.
Okay. So, and are you sure that in the classical case it depends on the mass?
Yes, because.
Okay. Because?
Yeah, because the potential is m omega squared, then.
Okay.
Then
okay, good. So
q squared, then divide by 2. Yeah.
Okay. So but so let's look at this here. Wait. So okay. Can you hold on to your question, because we're going to come to it in the next slide. Okay. Let me just finish, because it's going to come up. So okay. So so this is another example where so what they do is they measure the unfolding temperature. So the temperature at which a protein unfolds, and from that they can measure the free energy required to denature a protein. Okay, so this is a measure of the free energy difference between folded and unfolded states. Again, this is a configurational property of the system. And what you see here is that the delta G, when you go from H2O to D2O, changes significantly. And okay, free energy differences are related to ratios of partition functions. And in the classical case, those free energies should be independent of the mass. And so we're going to, we're going to see more clearly from the next slide why that is the case. But as a first glance of this should surprise you, because that's not what you expect from properties that are sensitive to the configurational, in classical case, do not depend on the mass. Okay, dynamics is a different story. Okay. Okay. Okay, so let's go. Yes. Okay. So now let's this relates to Paul's question. So let's go back now to our canonical probability distribution function, in the classical ensemble, classical limit. So the probability of finding the system at a particular set of positions and momenta is proportional to e to the minus beta potential plus kinetic energy. Okay, that's the statistical weight of the system. So now let's think about, I have a system moving in a Leonard-Jones potential or in a harmonic potential. It's vibrating in that potential with some mass. Now I want to know, and at some temperature, kBt. Now I'm asking, what is the probability of finding the system at a particular set of positions and momenta given this potential? And the statistical probability of finding the particle at some at a particular set of positions and momenta in the classical situation factors separately into the classical into the configurational part and the momentum part independently, only in the classical case. And so only the momentum part of the classical probability or partition function has a mass dependence, not the configurational part. And so in a statistical sense, if you were to look at the probability of finding two particles at a particular distance, so if we were to look at the probability distribution or the pair correlation function between two particles moving in a harmonic oscillator with some potential V, then the configurational part of the probability distribution would be independent of the momentum part. And so the momentum part in the classical case would just be, well, it would just be the boring Maxwell-Boltzmann distribution. And so in this part, there is no mass. Okay. And so in the context of these situations that I'm showing you here, where there's a shift in the density maximum, there's a change in the configurational property of the alpha helix, going from H2O to D2O. There's a change in the free energy difference between folded and unfolded state, going from H2O and D2O. The only thing that can cause this is a quantum phenomenon. So the breakdown of classical mechanics. Okay, and so in biological systems, like in where there's a lot of water, quantum effects associated with things like 0-point energy, tunneling, even at room temperature, play a very, very important role. They're significant. And they tie in then to very interesting electronic effects. Okay, because all these interactions involve fluctuations of protons, to which electronic degrees of freedom then also respond to. Okay, so this is an area that is still not so well appreciated in terms of the understanding of how it affects molecular forces and interactions. All we know from biology is that D2O does not sustain life. And so many of the processes that are relevant for biological function simply don't happen in D2O.
I think Paul a bit remember a bit wrong.
Yes.
Paul, I think he remember a bit wrong about harmonic oscillator. So because we have 1/2 omega square x square, so omega is square root of k over m. So m will be like they eliminate from the denominator. And
yes. No, thank you, Lian. Yes.
Yeah. So it doesn't depend on the
mass. It doesn't depend on the mass. Okay, thank you. Yeah. Okay. Questions? Okay, so let's now dissect this a bit better in terms of what are the factors that lead to enhance quantum effects. Okay, so in order to answer this question, we need to go back to h bar. Well, h bar omega. And omega are frequencies. So I have a system that has a spectrum of different frequencies. Okay, and high frequency modes, low frequency modes, and h bar omega is dictated by high frequency modes. And this is a typical frequency spectrum. It's a vibrational spectrum of water. And so focus on the blue curve. This is the experiment. So this is a vibrational frequency distribution of relevant vibrational modes that are present in water. And the highest frequency vibrational mode is on the order of 3,500 wave numbers, or equivalently, that translates into an energy of about 0.2 eV. Okay, that's a huge amount of energy. 0.2 eV is much larger than 25 milli eV. So the classical picture so I've been showing you here all up to now, all these pretty pictures of static classical OH bonds, these covalent bonds, but the 0 point energy of this guy is huge. And this is something that we began our discussion in these lectures right in lecture 1 about the uncertainty in the position of the protons. And this uncertainty is created by the underlying 0 point energy of the system. And because they are these biological systems are loaded with protons. Protons are light particles, so no surprise, quantum effects should be important. Now, what this means is that you have to go up to what's the number? You have to go up to let's see, 0.2300. You have to go up to about 600 Kelvin before KBT equals 0 point energy. Equals is similar to 0 point energy. So quantum effects will not play a role anymore, only when you get to those high temperatures. Okay, so and you know, okay, here I've discussed the OH bond, but you can do the same exercise for the NH bond of water, this of peptides, the CH bond. You know, they're all very sort of similar order of magnitude. Okay, so we should not be surprised that there are significant quantum effects even at room temperature that can lead to isotope dependency that go beyond the classical assumption. Okay.
Now, what is the temperature that you say the quantum effect will affect significantly?
At what temperature it will?
Yeah. At what temperature?
No, well, at any temperature where this is much larger, where the left guy is much larger than the right.
Mm-hmm.
So I have to make, if I remember correctly, I think the number is if you go up to about 580 or 590 Kelvin,
Mm-hmm.
before this becomes close to 0.2 eV.
Mm-hmm.
So as long as there's a big gap between thermal energy and 0 point energy,
KBT is 0.025
that's correct.
milli electron volt.
0.025
yeah.
eV, yeah.
Yeah, EV. So I thought room temperature. That is at room temperature.
That's correct. That's room
and
temperature.
And 0.2 already like larger than.
Absolutely, yeah. Yeah, that's the point. That at room temperature, 0 point energy is significantly larger than thermal energy. That's exactly the point.
So I still don't understand why you talk about 590.
No. So okay. So why I talk about it is so when can you use? So the question is the following: when can you use the classical? When does, let's say, water become classical? That's the question. And water becomes classical when 0 point energy is not larger than KBT. When KBT is larger than 0 point energy.
I see.
You see what I mean?
What you mean? Yeah.
Okay. So I bring this up because also I don't know what your, when I learned statistical mechanics, there's often a tendency to say, oh well, you take the limit of large temperature and the limit of large mass, than the classical.
Yeah.
And all I want to say here is that when you combine an understanding of well, chemistry, a bit of physics, it's very important to be careful about what do you mean by that limit, and that limit can be very different depending on what problem is, and it has an important implication in the case of biological systems.
Yeah.
Okay.
Thank you.
Good.
Yeah.
Thanks. Okay. So maybe I'll end with try to finish up these last two points I want to discuss. So, what's the physical change? What physically changes because of these quantum effects? Well, structure changes, and so here is a distribution. It's a radial distribution function of the OH bond, the OH covalent bond. And you see that the red, I don't know if this is red or not because I'm colorblind. This is red or green. This dashed curve here is localized at 1, sharply peaked at 1 angstrom. So this corresponds to the covalent OH bond, right? So if you, the distance, this distance here, so the probability of finding a proton near this oxygen, there'll be a big peak at 1 angstrom, because that's the typical length. And that's the classical, in the classical case. So if you did a classical Monte Carlo or molecular dynamics and you computed the pair correlation function, that's what it would look like. But now look at what is known from experiments. So the black, the blue circles, and you see that the blue circles are broader. And so the physical effect of 0 point energy is essentially, you can think of it as injecting more heat or kinetic energy into the OH mode. So it's hotter. And because it's hotter, it breathes and expands more. Okay, and so it's characterized by larger fluctuations. And so now you may say, well, this one, we're talking about 0.3, 0.2 angstroms. These are tiny differences. These are small differences, but remember, don't forget about the electrons. There are electrons floating all over these places in these bonds, and the electronic structure will adjust in non-trivial ways to these types of distortions that are happening. And so clearly a more accurate and physically sound description of the fluctuations in water and also in its electronic, let's say, density of states requires quantum contributions. This is sort of now very well established and appreciated. The second thing is on the momentum side. So in the classical world, the momentum, the proton, the velocities or the momentum of the protons obeys a Maxwell-Boltzmann distribution. Okay, classical. And so, and what you see here, these are experimental measurements from neutron scattering. I'm not going to tell you anything about this PI CPMD. This will come later, just the experiments for now. You see that basically what quantum effects do is they lead to a higher average momentum. So the physical picture that you should have in your mind is that an easy way to think of the role of quantum effects is you make the modes hotter, and therefore they are breathing more wildly. okay, leading to very subtle but significant changes in also in chemistry. Okay, and so I'll end with this, and I think this is mostly for the CISA PhD students, because it's I think it's related to the course that you're taking with Alessandro on sampling and coordinates, collective variables, etc., etc. So this is a very interesting paper that it's I also for the diploma students, I encourage you to read it. That was published by David Chandler on examining the free energy pathway of sodium chloride, so Na plus Cl minus, dissociating in water. And it's a very, very kind of a classical textbook problem that demonstrates the challenge, and also how solvent can couple into the underlying free energetics in very non-trivial ways. So look at the bottom panels here. The bottom panels here are the free energy along the sodium chloride distance in water. And so there's a minimum, a solvent separated minimum, a solvent partially solvent screen minimum here, where the sodium and chlorine are closer. And then as you move away, of course, there's a lower free energy because entropy wins. And the top panels show the two-dimensional free energy surfaces that lead to the same one-dimensional free energy along the sodium chloride distance. So this is the distance, again, on the x-axis. On the y-axis, it's some solvent coordinate, okay, some solvent reorganization. And what you see is that in this case, in case A, this bottom curve, the distance between the ions, does very well in separating out the two states, A and B, even in the solvent coordinate. But in this case, you see that there are many states that are actually in B, but they're put into A. And there are many states that are in A that are put into B. And so the solvent can couple in really, really non-trivial ways, especially in chemical reactions. Okay, and so this is just basically a teaser, an example of how this can happen. But I highly recommend that you take a look at this article, because it's very, very interesting. And I think they use also something called transition path sampling, which you have already probably learned about in Alessandro's class. Okay, I think I will stop here. So that's where we end for today. So today was a bit of an overview. Next week, we're going to go actually rewind the clock a bit and go back to even some more basics of water before going back to some applications. And in case any of you don't know, this is the Night White King. I forget his name now. If you haven't watched it, you should. It's very interesting. Good inspiration for the different phases of water. Okay, that's it from me. I promise this weekend I will create a Slack channel and put the slides up to today.
Yeah.
Okay.
Thank you.
Thanks. Have a good weekend, guys.
Thank you.
Thank you. You too.
You
Thanks.
too.
Bye.
Bye.